Hi everyone. Hey, let's talk about solutions. So in a previous video, we had a whole bunch of definitions dealing with solutions. Let's look at a few images and start working and playing around with some solutions. Okay, let me get the screen set up here. Hopefully that's not on your screen. Okay, so 3 topics in this video. We want to show how to prepare solutions, how to make dilutions of them, and another way of measuring concentration called equivalence. Okay, first thing first. Let's talk about how to make these solutions. I know video is probably not the best idea. We really need just to go in the lab and just do it. But it's a good idea to have an idea of what to do once we get the lab. So here's some images. Let's say you have to prepare a solution of, what is this, cobalt. So I want to put some cobalt ions in the solution. Okay, so the proper way of doing it is to first weigh out the quantity of cobalt. This is a cobalt chloride solid. There's 2 water molecules associated with these crystals of cobalt chloride. So when you calculate the number of moles, you have to add up all the atoms here. Use the atomic weights off the periodic table to get the molar mass. And if you know the weight, looks like it's 10 grams, you could then calculate the number of moles of cobalt on this little piece of weighing paper on the balance. Okay, and then you carefully put them into this container called a volumetric flask. Now we're going to use a volumetric flask anytime where we need to have careful and precise measurements of concentration. Now sometimes in lab, it's like, okay, we just want to see the experiment work, yes or no. So it'll be a little more sloppy and it'll be acceptable because we don't want really good accurate data. We just want to get the main idea. So we might use a beaker or a graduated cylinder or Erlenmeyer flask, any number of, or test tubes, any number of glassware to prepare a solution. But here, if you really want to do things carefully, get this nice, kind of expensive piece of glassware called a volumetric flask and put those crystals in there and use a funnel so you don't spill any of the crystals and rinse them into the container. Make sure none of those crystals get lost. Again, we're making it pretty accurately. And then what you do is you partially fill the container, volumetric flask in this case, and then you start swirling it to get all the crystals to dissolve. Okay, and that's what this step is over here, the swirling it until it's all dissolved. So it might take some time. And then you might add a little more water to help dissolve it a little more readily. And then once it's all dissolved, then you carefully, and I wouldn't squeeze in some water, I would use an eyedropper. Well, maybe I squeeze in some water to start filling it close to the mark, but then use an eyedropper and very carefully add enough water until the top of the solution, actually the meniscus. So water kind of sticks to glass. So the level of water isn't perfectly flat, it's kind of curved as the edges of the water kind of sticks to the flask, the glass. And what you want to do is look at the bottom, the lowest point of the surface. It's called the meniscus. And you want to line that meniscus, the bottom of the surface, right on that mark. It turns out these volumetric flasks are a little pricey because every single one of them are individually calibrated, meaning that someone marks, and probably with the use of a computer, automated system, but anyways, one by one, they precisely are marked at this, and there's a mark there, so precisely we know the volume is 500 in this case, 500 milliliters, and at least 1 decimal point. So it's probably, where's my pen? Whoops, I forgot to plug it in. So it should be about, not about, we should at least have 4 significant figures. Sometimes these can give you a 5th sig fig, another decimal place. Anyways, that's how you do it. You would also put a stopper on here and invert this a few times because the top of the solution would have just received fresh water and the bottom is still mainly the concentrated cobalt solution. So you want to make sure you mix this, invert it a few times to get it completely homogeneous. Well, those terms, make sure it's uniform throughout the solution. Cool. That's how you prepare a solution. You might actually see this problem on the test. So it's helpful for the visual learners to have this idea in mind. It's like, so if you see this question, maybe I should move it closer. Describe how to prepare 100 milliliters of a 2 molar sodium chloride solution. You might be wanting to think about this procedure up here and use those words in your answer. So you might say, okay, describe how to prepare 100 milliliters. Well, here is a 500 milliliter flask. So you want to use a smaller flask that only holds 100 milliliters. And now the concentration is 2 molar of not the cobalt, but of sodium chloride. But the procedure is the same, right? Go get some salt crystals, pour them on a balance till you get the right number of moles, put them in a volumetric flask, swirl it to dissolve with a little bit of water, and then add enough water to mark it off to the exactly, as close as you can, to the 100 mil mark. That's how you prepare the solution. Also, I would like to know, for full credit on this problem, how many grams are you weighing out? So you can get partial credit for using words to describe the process, and you get partial credit for calculating how many grams. And if you do both of those, then you get full credit. All right, so let's work this out. Okay, so what do we want? Well, we want to know how many grams of salt to put on the balance. So from the question, describe how to prepare 100 milliliters of 2 molar sodium chloride solution, there's no mention of grams. So you need to know, have an idea conceptually what is going on. How do you prepare solutions? Well, this top diagram shows you how to prepare them. Take some solid, dissolve it up, be very precise on the final volume. That's how you do it. Okay, so in that case, you have to just know that to prepare the solution, you need to start with some sodium chloride crystals. That's what we want, the quantity and the number of grams of salt crystals. And then we just use dimensional analysis, use unit conversion. We studied that in the first unit. So on the right side, find the unit that you want to get. What do you want? I want grams. And then over here on the left, start with a number that you know, something you've been given. So you just scan the question for digits. And here's 100, and here's 2. So one of those numbers is going to go over here on the far left. Choose the one that has a single unit. So use a single unit number and put it here. Okay, so 100 milliliters. Milliliters is a single unit. Ooh, but M, that looks like a single unit. Go back and review the video on concentration, and you'll discover this capital M is hiding 2 units. M stands for molarity, and the units are moles per liter. Yeah, there's 2 units with the number 2. Don't start with that one. Start with a single unit number, the 100. It only has the units of milliliters. Excuse me. Okay, step 3 is find conversion factors. We need to change ml into G. And so you might be looking, hey, isn't there a nice conversion factor with grams over milliliters? Those are the units of density. So you might be thinking, ooh, if I knew the density, I could convert it. That's actually true, but we don't have the density, unfortunately. So what else we got? We got molarity. Ooh, and molarity's got liters in it. There's a connection. So in the units of molarity, there's liters here, and we start with milliliters. So there should be a way to cancel out the milliliters, change them to liters, and then use this number to change the moles. Let's try that. So how do we get the milliliters to liters? Oh, you just have to remember that 1,000 milliliters is equivalent to 1 liter. It's equal to 1 liter. So that's a conversion factor I want students to remember, and that'll cancel out your milliliters. Okay, so that's just a conversion factor you gotta remember. And then now we can use the concentration. So we're gonna put in 2M into this part of our dimensional analysis process, but we wanna set it up so that the liters cancel out, and we're good. The liters shows up on the bottom, the moles comes up on the top. Keep the 2 with the top unit, And if you want, you can put a 1 here. These concentration units say precisely that 2 moles of sodium chloride is dissolved in 1 liter of solution. So 2 moles of NaCl in every 1 liter of solution. And we actually want to prepare 100 milliliters of solution. Good. Liters cancel out. We're left in moles. So now we need to find a way to change the moles into grams. We've done that before. What's the number that has units of grams per mole? Molar mass. Right? So you go to the periodic table and go get the atomic weights of Na, the atomic weight of chlorine, and add them up to get the molar mass. So we got a periodic table somewhere. Here's one. So we wanted sodium. There's sodium. If you look at the bottom number there, it's 22.9898 grams per mole for the sodium. Let's add it to the chlorine's atomic weight over here, element 17, 35.4527 grams per mole. Get out the calculator. Slide this up so I have some room. And then I got 58. Add those two atomic masses together. 58.44825 grams per mole. That's the molar mass of sodium chloride, meaning that if you have 1 mole, Avogadro's number of sodium chloride crystals, well, not crystals, but sodium chloride molecules, NaCl, they will all weigh 58.4425 grams. All right, so put that number up here. I don't know if I left enough room, but 58.4425, keep forgetting. Grams for every 1 mole. Good. And the moles cancel out. That gives us grams. Yay. Okay, so multiply all your numbers across. 100 times 2 times 58. Get a number, and then divide it by, well, multiply the bottom numbers together. 1,000 times 1 times 1 is 1,000. And then take the answer from the top, the numerator, divide by the answer from the bottom, and you should get, well, how many significant figures do we want? Well, you could choose 1 sig fig, or you could do a 3. I'm going to go with 3. Probably should only do 1, but yeah, it looks funny if I round off to 1 sig fig. 11.7 grams sodium chloride. Ooh. And if you walk away saying, yay, I'm done, darn it, you don't get all the points. The question said describe. So I would look at this answer and say, oh, good, you told me how many grams sodium chloride I need, but how do you do it? Please describe it. So you could just simply say, Dennis, dissolve 11.7 grams of NaCl in enough water to make 100 mils of solution. And I would then give you full credit. You told me the quantity. This is a great set of directions. Other students, if you want more directions, more details, if that's your thing, you can. You might say, okay, so this, let me just be clear, this gets full credit on my exam. If you take chemistry from another structure, they might want a little more detail. So place 11.7 grams NaCl as a solid in a 100 ml volumetric flask. Add some water. Swirl the mix. Swirl, such a scientific word. No, you could say just mix. Swirl to dissolve all NaCl, then fill with water to the 100 ml mark. There. Someone else might like that much detail. And all we're doing is just explain this process we got right up here. And we supplied this, the actual quantity of the weight we need of the crystals. Okay. One thing done in the video, we've prepared a solution. Okay, go over here. We're gonna look at dilutions next. Okay, a dilution didn't have as nice of a graphic. Nice simple one here. So you start with a solution. So molecules already dissolved in some solvent, probably an aqueous solvent. And then you add more water so that your final solution is more dilute. There's fewer molecules per volume. The concentration's gone down. And the visual here is, hey, if there's a lot of molecules, then it's a very dark color. And if you have fewer molecules per volume, it's going to have a lighter color, assuming that your molecules absorb light and have color. Okay, that's a way of doing it. And that's like the quick and dirty method, right? What volumes are you mixing here? Yeah, now just mix them together, make it less concentrated, more dilute. Okay, in the real lab, you might do something a little more precisely. Depending on the situation, you'd actually go into the stockroom. Well, you're not allowed in the stockroom. You go to the counter and say, hey, I need to prepare a dilute solution of hydrochloric acid. Well, you might say, well, what stock concentration do you want? We need a stock bottle from the stock room. You need a source of your solution, or maybe some sodium hydroxide. But you grab one of these bottles. Maybe it would be in the lab already. And then what you're going to do is carefully measure some out and take some out and put it inside the volumetric flask if you really want a precise measurement. Or maybe you might just put it in a beaker if you just need a ballpark estimate of the concentration. Depends on the experiment. If you're being careful, then use another volumetric flask. I can't see the mark here, but somewhere it's measured off to some volume. Can't read the volume, but that's how you choose which flask to get, depending on how much total solution do you need. But the whole process of dilution is take some of this out. That's going to be some volume. I'll call it V1. You start with some concentration, M1 molarity. So on the stock bottle has some concentration written on it. You can see that this bottle is 0.5 molar. This one's 1 molar. So look at the label and see what the current concentration is, and then take the proper amount out, and then add water, filling it to the mark. And now you have a new total volume. That's your V2, and it's at a new concentration. It's lower in concentration, M2. And chemistry majors, you need to memorize this. Science majors, it's a good idea. We do dilutions all the time in the lab. It's waste, they waste your time. You have to go and keep looking up the equation. That's not a hard one to remember. M1V1 equals M2V2. So you'll have the first concentration, your stock concentration from the bottle. The procedure you're using or whatever experiment you're designing will provide you with the concentration that you need. This is the diluted concentration, or the diluted solution. Let's just call it that. Your final solution. How about that? It's what's in your beaker or you're in your volumetric flask. And also in the procedure, you'll have some information saying how much do you need. And you'll probably make a little extra, so you make sure you don't have to make more if you spill some. So you have 3 of these numbers and you calculate the missing one. How much volume are you supposed to take out of the stock bottle? Cool. All righty, so that's the procedure. Take some of the concentrated solution from a stock solution. So just get used to that word. We're going to say, hey, this is the stock solution. We'll be told what the concentration is, that M1. And then this is the final, or your dilution. It'll have some final concentration and some final volume. And all you need to know is how much are you transferring of the stock solution so that you can prepare the right concentration in the right amount. So on your next exam, you might have this question or something like it. Describe how to prepare 10 milliliters of a 1 molar sodium chloride solution from a 2 molar stock solution. Okay, and so if I draw a beaker here, maybe you go to the stock room and they would take the stock bottle and just pour it into a little beaker for you. And they'll, just give you some quantity, hopefully enough. And then what you need to do is take that out and put it into another beaker, assuming you're not measuring this very carefully. That's your volume that you're transferring. And this is your M1, not V1. Your initial concentration, first concentration, take some of that first solution out, and then we add more water until we fill this up to the final volume with a final concentration. All right, so let's match things up. M1, V1, M2, V2. Okay, so what's the 10? That's the final volume of the dilution, the diluted solution. That's what we want to prepare. 10 milliliters, total volume, our V2 is 10. And this diluted solution, we need it to be 1 molar. Okay, and the stock, that's what you're starting with from the stock room. So 2M is your M1, 2 molar. And what you need to calculate is your volume that you're transferring. Now I picked these numbers so that some of you can just do this in your head. And I thought that'd be helpful just so you know in advance what the answer should be. And we can check our answer after we do the calculation, right? So we're starting with a 2 molar stock solution and we want it half as concentrated. You want to go from 2 molar down to 1. Well, that's half as concentrated. So what you should do is add 5 milliliters of the stock solution and add 5 milliliters of water. And you get a 50-50 ratio, and that would give you half as many molecules. That would reduce your concentration in half. That's the answer, just doing it in your head. So that's what we're expecting. We got all the numbers here. We have to recall the equation. It's M1V1 equals M2V2. And we'll put in our numbers. M1 is 2M, 2 molar. V1, don't know. M2 is 1 molar. V2 is 10 milliliters. Okay, there's 2 ways to do the algebra from this point, a long way and a short way. Who's going to do it the long way? No. Long way is to say, hey, in molarity, there are units of moles per liter. So you could change your milliliters to liters, multiply these together so you cancel out the liters and get the moles. That's a long way. The short way is just say, hey, I need to get my variable V1 all by itself. So let's divide both sides by 2 molar. And then these cancel out, giving you V1. And then molarity cancels out. Beautiful. No unit conversions necessary. So then you have 1 times 10 milliliters divided by 2. And that you can do in your head. 1 times 10 is 10. 10 divided by 2 is 5. 5 milliliters is how much you transfer. Ooh, I felt like I was done. I'm not done. The problem says to describe. All I did was calculate. So how do you do the dilution? I'll talk about this process right here. What you want to do is you want to transfer or pour, you can use your own words, transfer 5 milliliters of the stock solution. They use that word, so we can use it too, right? The 2 molar stock solution. You could say 2 molar, or you could just say stock solution, that'd be okay. 2 molar stock solution to a container, to a beaker, to a volumetric flask. I don't know, maybe we're gonna do it very carefully. To a volumetric flask or a beaker or a container and fill to the 10 milliliter mark. Okay, how come we didn't say add 5 milliliters? Well, it turns out that when you mix different solutions together, sometimes they can exotherm, they can heat up, sometimes they can cool off, and that'll expand or contract the volume. And sometimes there's no energy change, but the molecules, either by dilution or by mixing with the solvent, if you have different solvents, there can be some chemistry underlying there that can change the volume. So volumes aren't necessarily additive, they're kind of weird. So to hedge our bets and make sure we do the dilution properly, it looks like we probably have to add about 5 milliliters, but if there's some expansion or some contraction of the solution, as you're mixing in the water to the stock solution, we're not going to measure how much water we're adding. We're just going to measure the total volume at the end. So just add an eyedropper, add the water using an eyedropper until it hits the 10 mil marks, the 10 milliliter mark, and then you know you're good. You've added enough water. That's how you do dilution. Last topic, this one's a little weird. It's called equivalence. Anybody planning to work in the medical field? Or anyone planning to look at your lab reports after your next doctor's visit? Then you need to know about equivalence. Okay, so I guess I lied before. In my earlier video, I said, hey, there's 5 ways to measure concentration. They are molarity, which you know is moles per liter, mass percent, or weight percent, volume percent, mass volume percent, and parts per million. 5 good ways, depending on whose preference and what you're doing, what's convenient. 5 different ways to say, hi, how many molecules are here per quantity of solution? And now we got a 6th way. There's something called equivalence per liter, usually with a capital E. Do you remember we just did a problem with using milliliters? So you can talk about liters or milliliters. You can also talk about moles or millimoles. And so you can talk about equivalence or milliequivalence. And it turns out milliequivalence is much more common in the medical field. And you just use it the same way. How do you change equivalence to milliequivalence? Well, same way you change the liters into milliliters. Let's see, what do? You multiply by 1,000, right? 1 liter equals 1,000 milliliters. So then it's also true that 1 equivalent equals 1,000 milliequivalents. I figure some of you are asking, why is there a 6th method? Why is the medical field different from everything else we've been doing? The main idea is to measure charge. In a future video, we'll talk about charge and ions in particular, about how we have to keep track of those in either chemistry, biology, or in the medical field. So this will be convenient. Again, which unit of concentration do you want? The one that's convenient. So if you need to track the charges, equivalence is a very convenient unit to use. Okay, key idea is that an equivalent really means 1 mole of charge, either a +1 or a -1 charge. Okay, so what I got here are 2 beakers of water. Let's start dumping in some molecules so that we have equal amounts of charged particles inside. I'm not saying that correctly. Right now we just have pure water, H2O. That's a covalent molecule. There's no ions in here. That's actually a lie. We haven't talked about pH yet, have we? Can't remember. But water is in equilibrium with a small quantity of hydrogen ions and hydroxide ions. So actually there are some ions in here, but let's ignore that. So we have some pure water here, no ions. And then let's start adding some ions so we have some charge. So let's put in some sodium ions. Maybe it's sodium chloride, but let's only look at the positive charge. Let's simplify it. So we add some sodium chloride and then we're going to ignore the chlorines. And I don't know, somehow with our molecular tweezers, we're able to dump in 6 of these. So into the solution goes 6 sodium ions. And the whole beaker then has 6, maybe these are moles, I don't know, 6 moles of +1 charge. And over here, let's add some aluminum ions. Maybe it's also aluminum chloride, or we're going to ignore the chlorine. And let's only dump in 2 of these. So there's 2 moles of Al3 ions. But which of these beakers has more positive charge in it? They're equivalent. They both have 6 moles of +1 charge in there, right? So the total charge is, there's the 3 plus here, 3 plus there, a total of 6 plus. Over here it's a +6 also. They have the equal amounts of charge. If you're just counting how many plus charges, how many +1 charges, if you will, how many plus charges, they have the same amount. They're charged equally, equivalently. Yeah, I know, that's weird. But that's the idea. We're just counting how many charges, what's the total charge in our solution? Or rather, not total charge equivalence, but charge per liter. So if you have a whole liter, how much charge is in there? Sample problem. Yeah, let's get real. What's going to show up on our next exam? Well, maybe this question or something like it. There's a 4 molar solution of aluminum sulfate. There's a chemical formula. And it's asking, okay, so 4 molar aluminum sulfate contains how many equivalents per liter? All right, dimensional analysis. What do you want? I want equivalents per liter. Start with that, draw a line. That's what we want, equivalents per liter. What do we know? Well, the only digit in the question is a 4. And what are the units? M. We gotta break down the molarity into moles per liter. Ooh, you know what? We got sulfate and aluminum. We need to change this. How do I phrase it before? We have to know whether we're looking at the positive charges or negative charges. Turns out it's the same, but I should be more clear. So how about we say, the question might read, 4 molar aluminum sulfate contains how many equivalents of aluminum per liter? Okay, that way in the question you'll know, what does Dennis want? The positive charges and negative charges, because there's both in here. Okay, I want the positive charges. Okay, so then we're starting with 4 moles per liter of aluminum 2 SO43. That's what we're given. Now we need conversion factors that change the liters to liters. Okay, no change needed. In the denominator, we got the right units. We have to change moles to equivalents. Okay, and then the helpful thing we'll have to remember is that 1 equivalent equals 1 mole of charge, a +1 charge in this case. So what we have to do is change moles of this molecule into moles of +1 charge. I know it's weird. Let's just get, I don't see any pluses at all here, so let's break that down. When the molecule, a single molecule of aluminum sulfate dissolves in water, how many ions do we get out? Well, the aluminum separates into 2 individual aluminum +3 ions. That'll be aqueous. And then the sulfate, you get 3 of those. And then for this problem, we don't care about the sulfate. We're going to ignore that. But for every 1 mole of aluminum sulfate molecules, out of this big molecule will come out 2 moles of aluminum ions. Okay, we're getting closer. What are we aiming for? Equivalents. 1 equivalent is 1 mole of +1 charge. Okay, so if you have 1 mole of aluminum ions, how many moles of +1 charge is that the same as, equivalent to? 3, right? So to get the total amount of charge in 1 mole of Al3 plus, if we have 3 moles of +1 ions, these will have the same quantity of charge. Nice. Okay, more importantly, the moles cancel out the moles, and then this moles cancel out those moles. And now we have moles of +1 ions. 1 mole of +1 ions is the equivalent to 1 equivalent. That's the definition. Now we can cancel out that. And now we got our units, equivalents, and the liters didn't get canceled out. They're still there. Yay. So then it's 4 times 2 is 8. 8 times 3 is 24. And on the bottom, well, there's a 1 here, and there's a 1 there, 1 and 1. It's all 1 across. There's your answer. 24 equivalents per liter. And we're not asked to describe how to make it or anything. No, it's just a calculation. 4 molar aluminum sulfate contains 24 equivalents per liter. Right, so when I was a student, this is the one that was the weirdest for me. I struggle with this, I'll admit. So rewind the video a couple times if you need to, or try doing the homework and then come back to this part of the video and see if you can use dimensional analysis set up this way to solve those homework problems. And as you get more comfortable with the homework, you'll be fine on the exam. Definitely take a look at the sample test and get some practice there too. All right, let's end this video with an application, some reason, some motivation for why you might be interested in equivalence. So I did a little searching on the internet, stumbled across a blood thinner, heparin. Let's move this out of the way. Okay, so heparin is a blood thinner, right? So I'm not a doctor. I'm trying to think of why you might have to use that, but you know, certain cases. But heparin's a very common blood thinner. And so it's an injectable solution. Here's a little vial with the heparin dissolved in there, and it's not pure water. Turns out that if you inject pure water, there's a reaction at the site. Blood, tissue, fluid in the tissues is not pure water. So you're actually going to dilute the body, the bloodstream, or the tissues by injecting pure water, and then there's an adverse reaction. So it's very uncomfortable. So you need to have the same quantity of things in there. I'm needing the words. The words is osmolarity, and that'll be a topic of a future video. We have to think about osmosis. You may have heard of that, and osmolarity. In other words, you need to keep track of all these particles, all these ions and molecules, so you don't get this dilution effect or a concentration effect. Something's injected too concentrated, that can cause an adverse effect too. Anyway, it's important, right? Injecting stuff into people, you better be careful and know what you're doing. So this is part of knowing what you're doing. Okay, so for whatever reason the patient needs some heparin, it's dissolved in a 0.9% sodium chloride solution. Huh, that's cool. So this is not molar. Nope. It's probably, be convenient, sodium chloride is a solid and the solution is a liquid. So this is probably a mass volume percent. And if you check, oh, actually, let's go over here. So I zoomed in on the label. The sodium chloride was added 0.9 grams. And each 100 ml solution, yeah. So this 0.9% is actually a mass volume percent. Okay, what else is in here besides sodium chloride? Some dibasic sodium phosphate. That's a common name for dibasic. So there'd be 2 sodiums, 1 hydrogen. So that's sodium hydrogen phosphate. And then they add citric acid, and then they have some water. And those are the ingredients, and heparin, the blood thinner itself. Those are the 5 things: heparin, sodium chloride, the sodium phosphate, citric acid, and water. So 5 things make up this medication that's going to be injected. And we have to keep track of things. So if you want to keep track of the sodium, look at where all the sodium's coming from. The drug molecule heparin has sodium associated with it. You're adding sodium chloride. It's a salt water solution that we're injecting. This is changing the pH. We're going to pH balance this. So we have this basic compound with sodium in it. And then we have an acid, and the combination of the acid and base is going to adjust the pH to where we need it. 7.0, make it neutral. And then there's a tolerance range here. So these two components are there to adjust the pH. It's a buffer. We haven't talked about buffers yet in this class, but we will. It's kind of important for life. So essentially you have a buffer, you got the heparin, and then we have to add sodium chloride, so we minimize that dilution effect. Got to try and match the concentration of the injected solution with the concentration of liquids in the body. And let's see, so we got 3 sources of sodium: from the drug, heparin, from the sodium chloride, and then from part of our buffer, the sodium phosphate. So what if you want to know the concentration of sodium? Well, you could go and say, well, how many moles of heparin sodium do we have? How many moles of sodium chloride? How many moles of sodium phosphate? No. Total sodium. What do we got? And it's like, well, you can't use molarity. But I guess you could. It'd be weird, though, because some of the sodium is associated with the drug, which is a huge molecule. Some of the sodium is associated with sodium chloride, a tiny molecule. And then we got the buffer, a different molecule. Let's just use equivalents. So that's what they did over here in the electrolytes. Ooh, we saw that term before. Those are solutes that when they dissolve, they form ions. They're also solutes when dissolved, they can cause the solution to conduct electricity. So here are all the ions that are important here, and there's sodium measured in milliequivalents per liter. And the answer is 186. Well, you can calculate that if you go and look up. They don't list it here, so forget how I did this. I went and looked up the molecule heparin, and they tell you there's 200 units of it. So I had to go find a conversion factor and calculate that the sodium, number of moles of sodium from heparin is 0.0016. You can do this, 0.9 grams of sodium chloride, use the molar mass. It was 58 point something before. So calculate that to be 0.0154 moles of sodium from sodium chloride, and do the same thing for the phosphate buffer here. 0.43 grams were used. Add up the molar mass, add up the atoms, get the molar mass, divide by that, and it's 0.0016. And if you add them all together, there's the total sodium. Then each sodium is a +1 charge. So the total charge +1 charge is equal to this. And then why is it 186? Well, this is equivalents per liter. And what they did is they said, well, let's take one equivalent and change it to milliequivalents, multiplied by 1,000. So then we don't have to have any decimals on our label. Multiply this by 1,000, it's 186 milliequivalents. Cool. And it's just very much more convenient. It's like, how much sodium is in here? We'll measure it in milliequivalents, so we don't have to worry about where the sodium came from, because it came from 3 different molecules. Yeah, just tell me total sodium in terms of milliequivalents per liter. Cool. Hope you enjoyed that. I'll see you in the next video.